Hello everybody and welcome to this GCSE chemistry video about Group 0, or the noble gases. In this video we'll be looking at the properties of the noble gases, and we'll also be looking at some of the trends in these properties as we go down Group 0. And just to start us off, this is the group that we're talking about, Group 0, or sometimes called Group 8. It's on the right hand side of the periodic table, and these are the noble gases. Now this topic is quite short, so what I will do is I will weave little extra bits in from other topics in chemistry and also from physics, and that way we will see how these ideas link together. First of all, let's explore what the noble gases actually are. There is helium, the lightest of the noble gases, and then neon, next comes argon, krypton, xenon, and radon. The periodic table of elements, as set out by Dmitri Mendeleev or Lothar Meyer, had not allowed for the discovery of a group of elements between the halogens and the alkali metals. And so the discovery of an unreactive monoatomic gas, argon, by Lord Rayleigh and William Ramsay in 1895 came as a total surprise. And so I've said there that the noble gases are unreactive. Another word for unreactive, it means the same thing, is inert. I used the word monoatomic as well. And monoatomic is very similar to diatomic, except mono means one, and atomic still means atom. So these are not molecules at all, they are single atoms. And of course, they are all gases, hence the name noble gases. And because the noble gases are unreactive, it's no surprise that Mendeleev left them out of his periodic table, because he couldn't predict that there would be noble gases at all, because he had no evidence to base any predictions like that upon. Argon was discovered first, and that makes sense because it's actually the most common of all of the noble gases by quite some distance. In fact, it's actually the third most abundant gas in the atmosphere. We've got nitrogen, which is around about 78%, oxygen, which is 21%, and then argon comes in third place with just under 1%. Now, since these gases are unreactive, they are non-flammable, so that means that they won't burn at all. And you might think that since they are non-flammable, they don't react with things, you wouldn't encounter them in many different places, but actually that's not true at all. Helium, first of all, is produced in the sun when hydrogen atoms fuse together, and that's in a process called nuclear fusion that you'll encounter in physics. It's also, and a helium nucleus is also formed during alpha decay, because a helium nucleus is an alpha particle. So that's another physics link on here. A third physics link is radon gas. Radon gas is formed underground, and it comes up out of the ground, and it contributes to background radiation. And in fact, house prices are affected by the amount of radon gas that there is in a particular area. And the last use to mention of these noble gases is argon. And argon, because it's unreactive, and because it is the most abundant of the noble gases, it is used in light bulbs. And what it does is it prevents the filament in the light bulbs from getting too hot and reacting with oxygen, which it very definitely would do at the temperature that light bulb filaments get to. And in fact, on the subject of lights, neon is used in lighting itself. That fun red glowing lights, those are neon lights. And in fact, each of the noble gases actually does give out its own light when you pass electricity through it. So helium is a sort of a pink colour, neon is the nice red colour, argon gives a blue colour, krypton gives a pale green, and xenon gives a very pale blue. You wouldn't use radon in lighting because it's radioactive. And to finish off looking at introductory properties, I've just been talking about the colours that they give out when you pass electricity through them, but they are all colourless gases by themselves, and so it's no surprise that Mendeleev couldn't predict they were there and people didn't discover them very quickly, because they don't react with anything and you can't see them or smell them. And so it was only once we had developed electricity and really integrated into its use in science that we were able to discover these noble gases. Now, a little bit of a more specific property, and you need to know this for all of the different groups, but the pattern is the same for all of the different groups, but the relative atomic mass increases as we go down the group. And that makes sense for all the same reasons as the other groups. Each atom, as we go down, gets more neutrons and more protons, and it's the neutrons and protons that give atoms their mass. So as we go down the group, more neutrons and more protons. Another property that increases as we go down the group is the density. The reason density increases down the group can be explored if we look at what density is. Density is mass per volume. And an interesting property of gases is that if you have got the same volume of each gas, and if we use these two squares that are identical to represent volumes, and if one of them contained helium and the other one contained radon, if they were the same volume, so let's say they had a capacity of 1 litre, a volume of 1 litre's worth of gas, there would be the same number of particles of helium and radon in each of those boxes. And so, since each individual atom of radon is heavier than any of the others, particularly helium, the box on the right-hand side would be heavier because there is more mass contained in the same volume, because each individual radon atom is heavier than a helium atom, and there are the same number in each of these two identical boxes. That's one of the laws of gases. The same volume of gas will have the same number of atoms in it. Moving on to one of the most widely known properties of the noble gases, the fact that they are incredibly unreactive or inert. And the reason for this is all to do with their electrons. And you can work out the number of electrons by just looking straight at the atomic number. And it's also referred to as the proton number as well. But not only is it the number of protons, it is also the number of electrons. So if we work through a few of these, the good news for you is you don't have to go beyond argon in terms of working with their electrons, and that's because simply they get too big. But you need to be able to work with the first 20 elements. So helium has, of course, got 2 electrons because it has got an atomic number of 2. And so if we put a little plus in the middle to represent the nucleus of helium, we can just add those 2 electrons in the first shell, because as we know, the first shell can hold 2 and then it is full. So this shell is full. The electronic structure for helium looks quite weird because we are literally just writing the number 2, and that is the electronic structure, or sometimes called the electron configuration. If we move on and have a look at neon with 10 electrons, we won't be able to get away with just one shell here. We'll need to have 2 shells for our electrons. So here we go with 2 electron shells. So in the same way as before, we fill up from the middle and work outwards. So we put 2 electrons into the first shell. We've got 10 in total, so that's 8 more. And so we put those into the second shell, because the second shell can hold 8, and then it is full. So the first shell can hold 2, the second shell holds up to a maximum of 8 electrons, and then it's full. And so the electronic structure for neon is 2, 8. Last of all, argon. Argon has got 18 electrons. And so we are going to need 3 electron shells this time to fit those 18. The first shell holds 2, and then it's full. So we've got 16 more to put in. The second shell holds 8, and then that's full. So we've used a total of 10, so we've got 8 more to put in. The third shell also can hold a maximum of 8 electrons. And so we've got 8 more to put in, so this shell is going to end up being totally filled as well. So the electronic structure for argon is 2, 8, 8. And so you'll notice that argon and neon both have 8 electrons in their outer shell, which is full. And so this group is very, very nearly totally deserving of being called group 8, which is very logical because the one straight to the left of it is group 7. But because helium is quite small, this 2 electrons is also full as well. And so the 8 electrons in the outer shell is full, and the 2 electrons in the outer shell is full. So that 0 in the name for group 0 really serves 2 functions. First of all, it represents that complete shell of electrons, but actually historically it was referred to as group 0 because these noble gases don't need to form any covalent bonds to become stable. They already have a stable electron arrangement. So the 0 in their name means that they have got a valence of 0. They form 0 covalent bonds. And so to sum all of this up with the most important phrase that you're going to need, the noble gases are unreactive because they have a full outer shell of electrons, which gives them a stable electronic arrangement. Remember, the other elements in different groups, they give or take or share electrons in order to become like the noble gases, in order to achieve this stable electron arrangement. And that's something that the noble gases already have. And to return back to the word I gave you before, monoatomic, which meant one atom. So they go around by themselves as single atoms, and the reason is they don't need to bond to anything else to become stable. So they just are single atoms of whatever particular gas we're talking about, argon or helium or neon. One last interesting fact, the name argon encapsulates the concept of the noble gases because it comes from the Greek argos, which means idle or lazy, implying that it doesn't do anything, it is unreactive. The final thing we are going to explore in this video is the boiling points of the noble gases. I'll mention melting points as well, but boiling points is by far the most important because these elements are gases. The first thing that we notice when we look at the melting points and the boiling points is that they are really, really tiny numbers. They're all negative values. And so the melting points of helium is minus 272 degrees Celsius. That's very, very nearly as cold as it is scientifically possible to get. And then as we go down the group, you can see that the melting point does increase because the negative number gets smaller, but it is still really, really low. So all of the noble gases melt below 0 degrees Celsius. And since that's the case, there is no question about these elements being solids. They will absolutely all have melted at 0 degrees C. If we then move on to have a look at the boiling points, you can see they follow the same pattern, and in fact they are really, really similar as well. The boiling points are all below 0 degrees C. And so the conclusions that we need to make here is that the boiling point as you go down group 0. And not only that, the boiling points are all below 0 degrees C, therefore all of the elements are gases. I mentioned earlier about the uses for the different noble gases, and so it's worth mentioning how we extract the noble gases from the air. And we do this by fractional distillation, which you may have heard of. Fractional distillation is most commonly encountered when we are separating the different parts of crude oil, the different hydrocarbons of different lengths. And to do that, we vaporize the substance and then we condense the different parts of the mixture at different temperatures because they have got different boiling points. And we can do that for the noble gases as well. We can see that they've all got different boiling points, and so all we need to do is have our mixture of air here in some kind of container, and all we do is we gradually decrease the temperature, and as the temperature decreases, the different components in this gas mixture, they turn into liquids. Or to be slightly more scientific, they condense, and that means gases turn into liquids. Ignoring the other components of air, if we just focus on the noble gases, the noble gas that would condense first would be the one whose boiling point is the highest, and that's radon here. So radon would condense first, and then xenon, etc. And the helium would be incredibly hard to get it to condense. And so what we would do, if we wanted to separate this mixture of 6 noble gases, we'd cool it, we'd collect the radon, we'd collect the xenon, then the krypton, etc. And we probably wouldn't bother to condense the helium. Once we'd got the temperature to minus 247, we know we've collected the liquid neon, and so the helium would be whatever has been left behind. The reason why we see that pattern in increasing melting point and boiling point as we go down the group is to do with the size of the atoms and the effect that that has. As we go down the group, the atoms get larger. And what I've done on the left-hand side is I've drawn 2 atoms of helium, 2 atoms of neon, and 2 atoms of argon. Between all covalent molecules, there are intermolecular forces, and these intermolecular forces hold molecules, in this rare case atoms, close together. And the stronger those forces are, the harder it is to pull these atoms or molecules normally apart. And as you can see for helium, the atoms are small, and so therefore the surface area for intermolecular forces is quite small. That zigzag line is representing the intermolecular forces. Whereas for neon, the surface area of contact is a lot bigger, and so the intermolecular forces are larger. And then when we get onto argon, the surface area of argon is much greater because it's a bigger atom, and so the intermolecular forces are greater as well. And so boiling point increases down a group because the intermolecular forces are larger, and this is because the atoms are larger. And that pattern is something that you could expect to continue as we go down the group, and it does. I've just mentioned predicting properties based on some information. That's actually mentioned directly on your specification. So if we know information about some elements, we can predict properties of others. And I've actually already mentioned one of these properties, and so I'll just remind you of it. Helium, neon, and argon were all gases. And so a logical conclusion would be that therefore krypton, xenon, and radon will also be gases. A more complicated question would maybe ask, what is the boiling point of xenon? I should stress that you don't need to memorize any of these boiling points or melting points. You do need to be able to work with information that you're given. So for instance, the boiling points in degrees C of krypton are minus 153 degrees C and radon is minus 62 degrees C. The question might be, now, what is the boiling point of xenon given this information? And the first thing that we need to note is that the boiling point increases as we go down the group. And so without too much thought, we know that the boiling point must therefore be bigger than minus 153. degrees C, but also smaller than minus 62 degrees C. We can do better than that. What I would recommend in a situation like this is to work out what the difference is between these two and halve it. Or, perhaps even easier, just find out what the average is. So what do you get if you add minus 153 to minus 62? If you add these two numbers together, you get minus 215. And then if you divide this number by 2, you can find the halfway stage, which gives us minus 107.5 degrees C. So to whole numbers, I would predict that xenon would have a boiling point of minus 108 degrees C. And so that would be your final answer for this question. And that is actually the boiling point of xenon, so this gives us a spot-on answer. One final question could ask something really similar. What is the boiling point of krypton? But instead of giving you a gap, it's the next one in the sequence. And so you can't take a simple average and find the halfway point. What we have to do is we have to look at helium and neon and argon, and we work out how much on average it goes down each time. So the stage 1 is to find what the size of the gap is each time. So the first gap between helium and neon is minus 246 and minus 268. So we need to find the difference between those two. And that comes out as neon being 22 degrees C higher as a boiling point. And then if we look at the gap between neon and argon, we're finding the difference this time between minus 186, the larger number, and 246 this time. And this time the gap is much higher. This time the gap is 60 degrees C. And so stage 2 is to find out what the average gap size is. And that is just a simple average of 60 and 22. So to do that, we're averaging two numbers, so we just add them together and divide it by 2. And we get an average gap for those first two of 41 degrees C. And so the final stage is to apply the gap to the next part of the sequence. And so what we would need to do there is we would need to add 41 on to minus 186. And when we do that, we get minus 145 degrees Celsius as our answer for the boiling point of krypton. And that's not perfect. The true value is minus 153 degrees C. So it's not perfect, but it certainly is very, very close. And we're being asked to predict. We're not being asked to pluck the correct answer out of thin air. Just remember that there isn't a single right answer. There will be a range of acceptable answers. Okay, that's the end of this video about the noble gases. Thank you very much for listening. See you next time.